Swayam Prabha. Digital India. Educated India.
In my previous lectures, I have discussed about the stress strain behavior of cyclically loaded soil, and then I have discussed that what is G max, how we can determine the G max by using field test and the laboratory test. Then we have discussed that how we will determine the G second modulus by using the equivalent linear approach, and then I have discussed about the non-linear approach, and I have discussed only one simple non-linear model. And today's lecture I will start about the 1D ground response analysis. And before I start the 1D ground response analysis, that I want to give one more information, that how we can establish a relationship between the damping ratio and the second modulus, because in the equivalent linear approach we have discussed that how we can determine the damping ratio, and then how we can determine the shear modulus. And then we have already given one relationship which is proposed by Ishibashi and Zhang, where we will get that how we can correlate the damping ratio with G by G max. Okay. So, that G is G second modulus. Now, I will give you another relationship, or to determine the or correlate the damping ratio with the second modulus. So, I have discussed that how to calculate the damping ratio for a particular loop. Suppose this is one hysteresis loop. Okay. And this loop, you know that the shear modulus, if you see in this loop, the shear modulus is changing along this rule every point in the loop, okay, along this line stress strain plot. So, if you can see, this is the shear strain, this is shear stress. So, that means that is my G10. Okay. This is the slope of this line is G10 at any point. And I have already discussed the what is G max. G max is the if I draw the slope at the initial state portion of the curve, then that will give me the G max or maximum shear modulus. And actually the G is changing at every point along that stress strain curve. Okay. So, that is the your G10 tangent modulus, but the secant modulus is the average shear modulus of a particular loop. Suppose that this point I want to determine the G max. So, this will give me the, this slope will give me the, or if you go this side, this slope will give me the secant modulus. So, it is the average shear modulus along this for this loop. Okay. So, this that is your that way we that shear modulus that we will get, that is the equivalent linear approach. And then, so that shear modulus that I will determine is corresponding to this strain, say strain C, clear. And now, we know that we have already discussed that our damping ratio is equal to 1 by 2 pi, then your area of the loop divided by 2 area of the triangle. if the triangle, both the triangles are same. Okay. So, this is the triangle, clear, that I have discussed already. So, now if I write this is 1 by 2 pi and this is area of the loop, then my area of the triangle will be, if this is say shear stress C. So, the area of the triangle, that will be half into tau C into strain of that point. Okay. That is the area of this triangle. So, ultimately this will be 2 pi area of the loop into tau C into strain C. Now, from here you can see that G second is equal to tau C by the strain, shear stress by shear strain. So, my shear stress at that point, this point is equal to G secant into strain. So, I can finally write this is a loop divided by G secant into strain square. So, this way also we can correlate that damping ratio with the secant modulus for a particular strain. So, that means that this point, this will be the damping ratio corresponding this strain C, and then the shear modulus, secant modulus you can determine. So, in this way for every loop you can determine that, and then if you draw the backbone curve, then every point also you can determine that secant modulus and the damping ratio also. So, but the damping ratio calculation I have already discussed, that if it is very large strain condition, then you have to be very careful to use this equivalent linear approach to calculate the damping ratio. Okay. So, now I will start that 1D ground response analysis. Okay. So, now what is 1D ground response analysis? So, the ground response or ground surface motion are predicted by ground response analysis. There can be the 1D, 2D, 3D ground response analysis, but in this course I will discuss only the 1D ground response analysis. Now, the ground response motion, those are can be predicted by ground response analysis. It is required for development of design response spectra, because I have discussed what is design response spectra. Then the required for evaluation of liquefaction hazard and required to determine the earthquake induced forces acting on earth retaining structure. Because suppose if you have a so bedrock motion, you have measured the bedrock motion, okay, where your seismograph is placed there, you have measured the bedrock motion. Now, that bedrock motion, how it will go to the surface, and then from the bedrock motion data how we can determine the ground surface motion. Because why the ground surface motion is required? Because the liquefaction hazard, the liquefaction that will be occur in that soil layer. So, that means that we need to know that ground surface motion for to evaluate the liquefaction hazard. Similarly, our earthquake structure, that is also near the ground surface. So, where how much force is acting, earthquake force, induced force is acting, that also we need to know, and for that purpose we need the ground motion, prediction of ground motion. And then the required for evaluation of liquefaction hazard, required to determine the earthquake induced forces and the design spectra also. So, those purpose we need to know the ground surface motion. So, those can be predicted by ground response analysis. Okay. So, now 1D ground response analysis, what are the assumptions in 1D ground response analysis? So, that means here we are considering only the vertical direction, motion of the wave in the vertical direction. So, that is why it is in the 1D ground response analysis. So, it is assumed that all the boundaries are horizontal. Okay. All the boundaries are horizontal. The response of a soil deposit is predominantly caused by the SH wave. Okay. Waves are propagating vertically from the bedrock. So, that is why I am talking about that we are only considering the vertical motion of the wave. So, from the bedrock wave is propagating to the ground. So, in the vertically only, it is in 1D ground response analysis we are considering that. The soil and bedrock surface are extended infinitely. Now, this why the wave in this assumption we are only considering the vertically propagating of waves in the vertically from the bedrock. So, because if suppose if this is your ground surface and this is a particular fault, and this is say your source of earthquake. So, wave will travel, okay, and there are near this surface there are different layers. Okay. So, wave will travel and then it will there will be reflection, there will be refraction. So, that means, when it will travel ultimately due to the refraction of different layer. So, this motion will be vertically. Okay. So, this nearly vertical, this motion of the wave is nearly vertical, okay, because of this refraction of the wave when it will pass through different layers. So, suppose this is your site and it is nearly vertical. Okay. So, that is why we are considering that waves are propagating vertically from the bedrock to the ground. Okay. So, first before we start about this analysis part, we should know the definition of different things. So, that is first one is the free surface motion, the motion at the surface of soil deposit. Suppose if I draw this thing, suppose this is my ground surface and where this is the bedrock. Okay. So, this one, so this is called free surface motion. So, here you will get the, if this is the condition, then this is the your soil, then this is free surface motion. This location the motion is the free surface motion. Then that the motion at the surface of the soil deposit. So, this is the soil deposit, this is the surface of the soil deposit. The motion at the surface of the soil deposit is called the free surface motion. Similarly, the bedrock motion, the motion at the base of the soil deposit or at the top of the bedrock is called the bedrock motion. So, that means any point here. So, this is the base of the soil deposit or the top of the rock. So, this is called bedrock motion. Next one is the rock outcropping motion. So, the motion at the location where bedrock is exposed at the ground surface, that motion is called the rock outcropping motion. So, here which one will be the, so this portion, this motion you can see the rock is exposed to the ground surface. So, this motion is called the rock outcropping motion. And the next one is the bedrock outcropping motion. The motion at the top of the bedrock where the soil deposit is not present is called the bedrock outcropping motion. So, if I draw that, so here the soil surface is present. So, suppose another condition, this is the bedrock, but where soil is not present. Okay. So, in the such condition, so that means here it will be rock outcropping motion like the previous case, it is exposed to the ground surface. But now here it is the bedrock outcropping motion. Okay. So, I mean here the soil deposit is not present. So, these are the different types of motion. So, then free surface motion, bedrock motion, rock outcropping motion, bedrock outcropping motion. Now, first approach that I will discuss about the linear approach. So, there are three types of approach to get that ground surface motion. So, one is the linear approach, another is the equivalent linear approach, another is the non-linear approach. So, here there are different cases. I will discuss only two cases, that is the uniform undamped soil on rigid rock and the uniform damp soil on rigid rock. The first case that I will discuss is the uniform undamped soil on rigid rock. So, the process is same for all the cases, but this how we will get this multiplying factor, or we can say that is the transfer function. So, that I will discuss for these two cases. The first what I will get, that first I will get, suppose I obtain the time history of acceleration of the input motion or the bedrock motion. So, the bedrock motion, I know the acceleration time history. So, and in my module 2 I have already discussed how I will measure the your strong ground motion. So, ground motion, how I will measure that. So, that I have discussed that from the strong ground motion can be measured by accelerometer, or the weak ground motion you can measure by seismograph. So, those I have discussed, and from there I have given the equation. The equation, if you know that the relative displacement measured by the seismograph, that if we put in the equation, you will get the acceleration or the ground acceleration you will get. So, that means you will get a ground, obtain the acceleration time history for bedrock motion. Okay. So, that acceleration time history is this, the first plot is the acceleration time history for a particular bedrock motion. Now, from the bedrock I will get the ground motion at the surface. So, the ground motion at the surface is my output, and the input motion. So, that is input motion would be a bedrock motion, and output motion will be the ground surface motion. Okay, because that is my obtain the ground surface motion. So, that is the aim. So, ground surface motion is my output here, and the input is the bedrock motion. Okay. So, first I have that bedrock motion, that is my first figure you have, this is acceleration versus time. So, as I mentioned that you can measure the acceleration versus time, then from there you will get the velocity versus time, and then the velocity time history, then you will get the displacement time history. If you integrate for that acceleration, you will get the velocity, then if you do the further integration, you will get the displacement. Now, then once you get that bedrock motion, then compute the Fourier series of the bedrock motion. So, then you convert this time domain to frequency domain. Okay. You can use that, and then you compute the Fourier series, that I have already discussed. Okay. That you can do the Fourier transform, that to get the your time domain to frequency domain. So, that means I will get the Fourier amplitude versus the frequency. Okay. So, that I have already discussed in my module 2. So, now you will get the compute the Fourier series of the bedrock motion. Okay. You can use the first Fourier transform, that you will get the time acceleration time history to Fourier series or Fourier amplitude versus frequency. Okay. So, from time domain to frequency domain. Then you compute the transfer function that relates the ground surface motion to the bedrock motion. So, now you have to calculate the transfer function that will relate this ground surface motion with the bedrock motion. Okay. So, that transfer function is given. So, that transfer function you plot with respect to frequency. So, you will get this curve. Okay. So, now here this is the third step to get the transfer function. Then the compute the Fourier series of the ground surface motion as the product of this transfer function and the Fourier series of the bedrock. So, that means, this is my first acceleration time history of the bedrock, then the Fourier series of the bedrock, okay. Then this is the transfer function which is correlating the ground surface motion with the bedrock motion. Then you multiply that this Fourier series of the bedrock motion with this transfer function, then you will get the fourth curve, which is the Fourier series of the ground surface motion. Okay. So, now compute the Fourier series of the ground surface motion by multiplying or product of the transfer function and the Fourier series of the bedrock motion. Okay. Then obtain the time of acceleration time history of acceleration of the ground surface motion by inverting its Fourier series. So, that means, you will get, now you will do the inversion of the Fourier series, that also I have discussed, that IFFT. So, that means, that if you inverting the Fourier series, then you will get the acceleration time history for the ground surface. So, this is the whole process. So, from the bedrock motion, I will get the ground surface motion. Clear? Now, here this Fourier transform, that how you will get the transform the or transfer that time domain to frequency domain, that I have discussed. Then I have discussed from the again from frequency domain to time domain, I will get how we will come back. So, that is also been discussed. So, now this transfer function, how I will get the transfer function, let me discuss that thing. So, that I will discuss for two cases, as I mentioned. First one is the uniform damp soil on rigid rock. So, let us do that. Okay. So, first one is the uniform undamped soil on rigid rock. Okay. Suppose this is that soil layer, that uniform soil layer, this one is the bedrock. Okay. And it is based on the assumption given, it is based on SH, shear wave, and the harmonic horizontal motion of the bedrock is given. So, that is why here it is moving in the vertical direction. Okay. It can move, it is moving vertical direction, but can go to vertically up or it can go to down also. So, if it is going vertically up, then that movement is represented by A into I omega t plus k z, and if it is down, then B into I omega t minus k z. Okay. So, this is harmonic horizontal motion of the bedrock another it is shear wave. Okay. Now, the response or the horizontal displacement. So, if you say this is my horizontal displacement, we will get A e to the power minus omega t plus k z plus B e to the power minus omega t minus k z. Clear? So, now where you know that omega is equal to circular frequency of the ground shaking okay, and k is equal to wave number. Which is basically omega by V s. What is V s? V s is the velocity of shear wave. Clear? And A and B, these are the amplitude of the wave velocity, wave traveling, the wave that is traveling in the minus z, that is upward, and plus z, that is downward direction respectively. Okay. So, that means I will get the horizontal displacement or the response, that is A E I omega t k plus k z plus B E I omega t minus k z. Now, at z equal to 0, that means at the ground surface. Now, my shear stress will be equal to 0 and shear strain will also equal to 0. So, if I know the displacement, then I can get the strain also, and if I know shear strain, if I know the shear modulus, then I will get the shear stress at any point, okay, at any depth. If I know the displacement, then you can see this is the function of t and the z, both function of t and the z. So, and what is this? Z is basically this is the vertical direction. Upward is negative, downward is positive. That is the common thing that use in the soil mechanics. So, or foundation engineering. So, that means here you can see that if I know the displacement, then I will get the shear strain, and if I know the shear modulus, I will get the shear stress from the shear modulus. If I multiply with the shear strain, I will get the shear stress. Okay. So, now that is my shear stress is equal to 0, shear strain will be also equal to 0. So, that is shear stress and shear strain. Clear? So, I can write that tau 0, z equal to 0 and t, that is tau is actually z comma t, the function of z as well as t. because I can get the shear stress at any depth at any time. Okay. So, that means at different depth I will get the shear stress time response also, shear strain time response also. Okay. So, and if I know the G at that soil. So, now if I get this tau shear stress at Z at any time, where the Z equal to 0, then that will be equal to G and shear strain at Z at any time. So, that is equal to G and shear strain will be del u 0 t by del z. So, if I know the displacement, because this is the expression of the displacement, from there if I do the del u del z, I will get the shear strain. Clear? Now, here remember that this G I am using the G max. Okay, here, because when I will talk about the G for linear approach, then it will be G max. When I will talk about the G at nonlinear approach, it will be G sec. When I will talk about the G at when I will talk about the G at for the linear approach, it is G max. When I will talk about the G for the equivalent linear approach, then G sec. When I will talk about the G for linear approach, it will be G tan. Okay, that I have already discussed in my previous module. So, here it is linear approach I am talking about. So, G will be G max, okay, maximum shear modulus. This is G max. Okay. So, now here this is I will get that value. So, now here this will be equal to 0, because that is the case we have considered at the surface your tau is equal to 0. Okay. So, now if I put this thing, then for G into del u 0 t del z, that means here if I do the del u del z, then that will be here, you know that this E I omega t plus k z, I can make it E I omega t into E I k z, and I am differentiating with respect to z only. So, that means I omega t is constant, okay, it is not changing. So, I can take this thing outside. So, E I omega t I can take outside, and then this will be A e to the power I k z minus B e to the power I minus I k z. Then there is a I k is there. So, this I k will also be here, I k, okay, and there is a G term also. So, it will be G I k. So, it will be G I k is coming from here. If I differentiate that E I k z, so there will be I k will come. If I differentiate that, so there is a G term, and e to the power I omega t, that is constant, that is outside. Within the bracket, it will be A e to the power I z k, and there is a minus I k z. So, this will be minus B e to the power I z k. Okay. So, this if I differentiate it, I will get this expression. So, in my next class, I will continue from here, and then I will show you that from here how I will get the transfer function for this particular case. Thank you.